Hello, algebra students. This lesson is going to be all about equivalent equations. There's a warm-up question on the screen. Now, it does say your teacher will assign you one of the following. I encourage you to pick whichever one looks more fun to you. If you want, you can also do both. But you will use at least one of these expressions and evaluate when n equals 5 and n equals 7. That word evaluate just means figure out what it equals if n is 5 and figure out what it equals if n is 7. Go ahead, pause the video, and try that now. I paused myself and I'm almost done. So when I evaluated both of these expressions for 5, my work is below. The green one is this first one, and I got the answer 8. And the blue one is the second one, and when I substituted 5, I also got 8. I'm going ahead and I'm working on the number 7 now. So the purple one is our first expression, and when I substitute 7, I got 20. Guess what I'm going to get when I substitute 7 into the second expression? Do you have any guesses? Well, it would say 7 plus 3 times 7 minus 3. I'm going to go ahead and write 4. And then 8 minus 3 times 2 is 6. That will give me 10 times 4 divided by 2. 4 divided by 2 is 2, and 10 times 2 is 20. So you might be noticing, even though these expressions up here, to my eye, look very different, right? We're getting the same answer each time. If I had asked you to evaluate those two expressions when n equals 100, now I don't know that answer immediately, but I do know that this answer and this answer would be the same. That is because these two expressions here are what we call equivalent. Equivalent expressions are expressions that might look different, but they actually give you the same result. Now, if you had me for developmental math, you heard this word equivalent when we talked about fractions. Equivalent fractions are two fractions that look different but represent the same amount and have the same answer. Expressions are similar, and what we're talking about today is something called an equivalent equation. We will give a definition of that in a couple minutes, but you can use this problem right here to get an idea of what it might be. Our goal in this lesson are these two statements down here. The first is I can identify what mathematical moves create equivalent equations, and we will talk about what that looks like. The second one is I can identify if two equations are equivalent and explain why or why not. You just know we love asking you to explain why something is equivalent or not equivalent. To get us started, I'm going to take us back to this table from a previous lesson. This was in the second lesson we did in this class, and one of the things we had done when we looked at this table was talk about patterns. Patterns we saw in the table and how you can use those patterns to write equations. And for this table in particular, one of the things we noticed is there was a lot of different patterns people saw in the class. First, some people noticed that every single time you add these two values together, it gets you to 400. That was true for every single set of numbers in our table. And so because it was true every single time, that could be a pattern. We used that pattern to help us figure out one way we could represent this represent this table is with the equation x plus y. I'm adding these two values, and when I do, it equals 400. We also had drawn a picture of what this story is talking about. I'll go ahead and pause real quick to draw the picture. So I've got my picture up here where it was talking about your distance from home and school. And so, for example, I use 75 and 325, saying if you've walked 75 miles from home to school, you're still going to have 325 more miles to walk. And that's because that total distance there is 400. I said miles, but not miles, meters. 400 meters between home and school. That's what this first equation here is saying. But not everyone in the room noticed this addition relationship. I'm going to leave that first one there as a reminder. But some people noticed instead of addition, you could use subtraction. Some people saw that if you had 400 and you subtracted this first value, it gave you the second value. And again, because that was true for every pair of numbers in the equation, that could also be a pattern we notice. Some other people in class noticed that if you take 400 and you subtract that first value, the meters from home, it gives you the second value. It gives you your meters from school. Again, if we look at this picture, that can make sense. We've got that total distance we would need to walk is 400 meters. And if you subtract out that distance you walk, for example, 75, it tells you how much distance you have left to walk to school. And again, some people noticed a different relationship from this table. The final one we heard in class is similar to the second one with subtraction, but in a different order. So for example, with this third value, some people noticed that if you do 400 minus 272, it gives you 128. Or 400 minus 4 gives you 396. And again, a summary of that could be 400 minus the distance from school would tell you the distance from home. In our picture, if you take that total distance of 400 and you subtract what you still need to walk, it would tell you what you've already walked. And one of the things we identified in that lesson really early on in this unit is that you can have multiple equations that correctly represent the situation. If I wrote an equation like this green one and wasn't sure if it was correct, I could use solutions to help me identify that, yes, this correctly represents this relationship. I could use, for example, any of these pairs of numbers, like 75 and 325, substitute them in my equation, and know, yep, this one correctly matches this information. We notice there are multiple correct equations. And when you have multiple equations that look different but are still describing the same relationship and still describing the same solutions, we call these equations, you can probably guess it because it's the name of the lesson, equivalent equations. Equivalent equations are just equations that have the same solutions. Now, we can have equivalent equations like the ones above here that have two variables. I know when my equations have two variables, it means there can be more than one solution. Now, this table had 5 pairs of numbers that are solutions, but we know there are many, many more. You can also have equivalent equations that only have one variable. So something like, I'll give you another example here. Something like 2x plus 5 equals 9, and the equation 2x equals 4. Those are equivalent equations because they would have the same solution. If I solve this first equation, I would have x equals 2. And if I solve the second equation, I would have x equals 2. They've got that same solution. And in this situation, there is only one solution that they share because there's only one solution to the equation. So going back to our goals for this lesson, we said our job is to figure out what mathematical moves can create equivalent equations and if we can identify if two equations are equivalent or not, and explain why. For example, in this problem here, when you were creating these equivalent equations, we were having to reset our brain each time and think about how you could think of the pattern differently. But there are some mathematical moves you can do to create these. So that's one of the things we're going to talk about. And then the second thing, we're going to talk about if I gave you these two equations, if you could identify, yes, they're equivalent or no, they're not. The first thing I want to do is I want you to practice coming up with equivalent equations. So down here, I have 2 more stories. They're about 2 different families here, and your job is going to be to write as many equations as possible. I would pause this video. My suggestion is maybe take 3 minutes, to see if you can come up with as many equations as possible for each of these stories here. Come back to the video when you're ready to see some answers. So for family A, I'm told there's 2 children, the youngest child and the oldest child. I know the oldest child's age, but I don't have an exact answer for the youngest child. It just tells me the youngest child is 7 years younger, but that's not a specific age. Because I don't know this, this is going to be my variable, and I'm just going to use y to represent the age of the youngest child. When I go to write my equations, there's a couple different ways you can do this. I can say my oldest child, who is 18, if I were to subtract 7, that would tell me the age of the youngest child. I could also say, well, if I start with the youngest child and add 7, that would get me to the oldest child, who is 18. You can also do the difference between the oldest child and the youngest child is 7 years old. All of these are correct equivalent equations that represent this story. If you were unsure about your equation you wrote, you could use the fact that they all should have the same solution. If I solve this first equation, it gives me y is 11. If I solve the second equation, it gives me y is 11. And if I solve the third equation, it gives me, you guessed it, y equals 11. Anytime you're working with equivalent equations, if you're unsure, which a lot of us are when we start this, if you are not confident, you can use a solution to help you know that they are indeed equivalent. For family B, we can do the same thing. The difference here in the family B story is I don't know the age of either child. It just tells me the middle child is 5 years older, but that's not a specific age. So I'm going to use M for the age of I'm just going to do middle child. And then I can also say, I don't know the age of the youngest child. So let me use a different variable than I did up here. Let's use C for the age of the youngest child. Here, it's giving me that description that the middle child is 5 years older. So when I go to write my equation, I can say, well, if I start with my youngest child and add 5 years, that takes me to my middle child. And look what I did. I used y for youngest child. Now, I think family B, when I teach this in class, usually everyone agrees that one was a little harder. And it's harder because you don't know as much information as you did up here. It can help for you to think of a possible solution. I don't know the exact answer here because I've got 2 variables, but I could come up with a possibility. For example, if I say my youngest, pick any age you want. I'm going to say my youngest is 10 years old. How old would the middle child need to be? Well, the middle child is 5 years older, so the middle child would need to be 15. Now, this is just an example. I don't know this for sure, but I did that because now I have a pair of numbers. Now, I could say, well, if C is 10, my middle child must be 15, and check to make sure that pair of numbers works in this equation. And if you substitute in 10 for C and 15 for M, 10 plus 5 gives you 15. That helps me know that this equation would correctly represent this family. Now, just like we saw above, this is not the only possibility. I could say, well, the middle child is older. If I take the middle child's age and subtract 5, that gets me to my youngest child. And again, I could use 10 and 15 to help me check that this equation is correct. I want to give you an example of how this pair of numbers really can help. Maybe you write down something like M plus C is 5, and you're not sure if that's a correct equation. If you know a possibility is if the youngest child is 10, the middle child's 15. And remember, it doesn't have to be that. Your youngest child could be 1, and then that would mean your middle child, if they're 5 years older, would be 6. You could use any pair of numbers, and if you put those into the equation, M is 6, C is 1, it lets us see that does not come out to be true. and it helps us know that equation is not right. We could do that with some other situations. For example, if I said C minus M should be 5, I think if we substitute those numbers into the equation again, I'm going to use 10 and 15. It would say 10 minus 15. You might be tempted to say that's 5, but that's negative 5, so that is not right. However, if I switch it around, M minus C equals 5, M could be 15, 10, or C could be 10, and yep, that's correct, which helps me know that is also a correct equation. This equation is just saying the difference minus the difference between your middle child and your youngest child is 5 years old. I've got a lot of stuff down here for the second one, but I'm going to circle the 3 equivalent equations we came up with. Are these 3 equations here? The goal of this first part is to emphasize what it means to be equivalent equations. And we said equivalent equations look different, right? All of these equations are not identical. They're using different math. They've got a different order in their equation. They look different, but they all share the same solution or solutions. Now, we said our goal for today was for you to be able to identify if 2 equations are equivalent. One way you can do that is by using the solutions, is by saying, well, they have the same solution, so they are equivalent. They have the same pairs of solutions, so they are equivalent. The other thing we talked about today, though, are the mathematical moves that you can make to create equivalent equations. In part B, sometimes it's hard for students to come up with any equations, but a lot of times students only come up with one equation. It's hard for them to think about the story in a different way. And the good news is you don't have to reset your brain every time to come up with a new equation. There's ways to use math to come up with these other equations. And that is going to be what the second part of this lesson focuses on. When we talk about what mathematical moves you can make to create equivalent equations, go back to what mathematical moves you learned when you talked about solving equations. So, for example, without fully solving either of these equations, would these 2 equations have the same solution? Explain why or why not. The way we can explain that is by figuring out what mathematical move you have to do to get from one equation to the next. Now, for example, I learned that when you solve equations, that you are allowed to add or subtract the same number on both sides. So, for example, when I learned about solving equations, I learned that if I want to get rid of that constant, that minus 5, I'm allowed to come in and add 5 on both sides. And notice if I do that, it gets me to that second equation. So when I'm trying to decide, would these have the same solution, I'm thinking about what math did I do to get from one equation to the next, and am I allowed to do that? Well, absolutely. You are allowed to add the same number on both sides. This is, I'm going to write the word allowed, or to use the name of it's an acceptable thing to do. I am allowed to do this. And so, absolutely, it means that this equation and this equation are equivalent. And because they are equivalent, they would have the same solution. So this is the process we're going to be doing in the second part, trying to figure out what mathematical move they made. Is it allowed? Is it acceptable? Is it legal? Can I do that? And if I say yes, it means they're equivalent and that absolutely they would have the same solution. For that explain piece, I could just explain it by saying you add 5 on both sides of the first equation and it gives you the second equation, and that is acceptable. So I've got a couple more pairs of equations like this where this is what we're going to be doing. We're identifying, are they equivalent? Do they have the same solution? And so these are the 5 pairs we're going to look at. We've got for each pair of equations, identify what mathematical move was done to get from one equation to the other. Are they equivalent equations? Would they have the same solution? Now, there's one other thing I want to mention before we start working on these. Up here, I had talked about what I learned from solving equations. But when you're looking at pairs of equivalent equations, the math they do to get from one equation to the equivalent equation isn't always a move you would do if you were trying to solve it. So think about the math we learned you can do in solving equations, but sometimes your equivalent equation is going to look more complicated. And so as we're looking down here, some of these second equations in the pairs look a little more complicated. We really want to be focusing on what math was happening. I'm going to encourage you, this first one here, go ahead, pause the video and try just this first one. Remember, you're trying to figure out what math they did. Are we allowed to do that? And then using that to help you answer the questions, are they equivalent and would they have the same solution? For this first pair of equations, if I'm trying to identify what mathematical move was done, I'm really going to focus on what changed in the equation and what stayed the same. So for example, the 10 did not change. The location of the equal sign did not change. The only part that changed was over here. That 4 and then the parentheses x plus 2 changed to 4x plus 8. And so that's where I'm going to focus trying to figure out what they did. Now, I have learned that if you've got a 4 in front of parentheses like this, that means multiplication. It means you need to multiply 4 times x and 4 times 2. And when I check, that's exactly what they did. That's how they got 4x plus 8. Now, are we allowed to do that? Absolutely. That's just what we call simplifying. So they simplified this left side here, and you are allowed to do that with an equation. So to answer the question, are they equivalent? Well, yeah, they are allowed to do this. And so yes, they are equivalent. The second equation is, would they have the same solution? The answer is yes, they would have the same solutions. If you picked a pair of numbers that works for the first equation and you substitute them into the second equation, it would also work there. And I said a pair of numbers, but I think there's only one variable there. So if you solved the first equation, it would have the same solution as the second equation. Now the second pair of numbers, that does have 2 different variables, and so your solution would be a pair of numbers. Looking at these 2 equations, though, it's a little more complicated. If I do that same thing of checking to see what has changed between the 2 equations, everything has changed. A 6 became a 2, a 12 became a 4, a 9 became a 3. So I'm thinking through what math could I do to make 6, 12, and 9 change to 2, 4, and 3. And you can try a couple different things. So I've had some people say, oh, like, well, 6 minus 4 gives me 2. Now I would have to be subtracting 4x there, but notice that didn't happen over here on the other side. And I know when you subtract 4x on one side, you have to on the other. Looking here, you figure out that the math they did was they were dividing. If you take, and I'm going to copy down the equation here, 6x plus 12y equals 9, and you divide both sides of your equation by 3, that gives you 2x plus 4y equals 3. Now, we don't often see this in pre-algebra, but are you allowed to do this? Are you allowed to divide both sides by the same number? Absolutely. And so looking at these 2 equations, they would be equivalent because you are allowed to divide both sides of an equation by a number. And if they are equivalent, that means, yes, they would have the same solution. So here are 2 different examples of what equivalent equations might look like. Now there are 3 more pairs of not equivalent equations, but 3 more pairs of equations. Go ahead, pause this video, and you're working on these 2 questions. Would that pair be equivalent, and would they have the same solution? Go ahead and try that now. Okay, going through these last 3 pairs of equations. For this third one here, what I noticed that changed is that the left side of the equation has this +1. Now, when you think about pairs of equations, can you add a number only on one side of the equation? No. If you want to add 1 on the left side, you also need to add 1 on the right side. So this pair they have is not equivalent because you are not allowed to add 1 only on one side of the equation. And because they're not equivalent, they would have different solutions. Now, I will give a pair that is equivalent. For example, 5x equals 10 and 5x plus 1 equals 11. Those would be equivalent because there you can see I added 1 on both sides of the equation. For the fourth pair of equations here, what I see that changed on the left side, 3x changed to 5x. That 9 stayed the same, but in the second equation, it also says plus 2x. That plus 2x can help us figure out what they did to go from a 3x to a 5x and to go from no x's to 2x. They added 2x on both sides of the equation. If you do that, 3x plus 2x gives you 5x, and 9 plus 2x gives you 9 plus 2x. Remember, you can't add a number and a variable together. Now, this one here, when I teach this in person, really sometimes makes people think. They're like, why would you add 2x on both sides? That's not going to help you solve that equation. I know, but remember, we're not trying to solve these equations. We're just trying to come up with a different equation that would have the same solution. And you are allowed to add x's on both sides of your equation, as long as it's the same amount, like 2x and 2x. So this pair here would be equivalent, and they would have the same solution. Now remember, if you're ever not sure of your answer, you could solve both of these equations and see that they both have the same answer, x equals 3. But our goal here is, if you notice what math they're doing, that's going to save you so much time because you're not going to have to solve all these equations. There's one final one here. We go from 2x plus 3 equals 5y to 4x plus 6 equals 5y. Now, the first thing I'm noticing, both of the equations have 4y. On the left side, we're just going from 2x plus 3 to 4x plus 6. How do you go from a 2 to a 4 and a 3 to a 6? You had to multiply the left side of this equation by 2. Now, think about what you know about solving equations. Are you only allowed to multiply one side of the equation? No. If you want to multiply, you have to multiply both sides. So this right here is not allowed. It is not acceptable, which would mean these two equations are not equivalent, and they would have different solutions. Now, again, I'm going to make a suggestion of what could be equivalent. Something like 2x plus 3 equals 5y. And if I wanted to multiply by 2, I have to multiply everything. It's kind of like the second one with the division, only we're doing multiplication instead. If you multiply everything by 2, you get 4x plus 6 equals 10y. Now, those two would be equivalent. So to summarize, if you're trying to make an equivalent equation, you can simplify it like this first one. But all of these other four, what they had in common is we were talking about you have to do the same math on both sides of your equation. You can't only add 1 on the left side. You can't only multiply by 2 on the left side. But you could divide both sides by 3. You could add 2x on both sides. You could add 1 on both sides. You could multiply by 2 on both sides. It goes back to when we had talked about solving equations. Whatever you do on one side, you need to do on the other. That is how you can identify equivalent equations, by the mathematical moves that were done, and not have to go in and solve. This was the final question in this lesson video. I hope you found this helpful in understanding what equivalent equations are and how you can identify if something is equivalent or not. Please make sure you do that homework, because this is one of those skills. The more practice you get, the more confident you're going to be at making these identifications without having to solve. Thanks so much for watching, and have a great rest of your day.